All right, good evening, everyone. This video, we're going to work through simultaneous multiple regression, and we'll work through a hierarchical regression model in Stata, working through some output, and working through interpretations on these data here in this example. And so the data that we're going to be using is going to be our regression exercise set. We've worked with this in a couple of different examples. Recall that what we've got is a large sample of motor vehicle accident survivors, and what we're looking at is the influence of PTSD, pain, opiate use as a dichotomous variable, 0, 1, no, yes, on a role functioning variable. So looking at adaptive functioning in day-to-day activities. Now recall when we went through and screened these data, we had some problems with the distribution of role functioning. It had a pretty severe skew and it's categorical, and so we went through and executed a natural log transform, which improved it a little bit. It's still not great, but it'll work for our purposes here. So our models that we're going to be running here, we're going to be regressing the natural log of our role functioning variable onto pain, opiate use, and PTSD. So as we're working through these, make sure that you have the handout and the output up and running, also to take notes and follow through with the example here. Okay, so I've got Windows set up, and so we have our participant numbers, pain, opiate use, PTSD, and then here is our natural log of our role functioning. Everything else is variables that we went through and used for screening stuff, so we won't worry about that here. So we've already screened, we've already taken a look and determined that these data are at least reasonable to go through and take a look in a regression model. So what we're going to do pretty quick and easy in Stata is we're going to go through and just run our simultaneous regression. And so here what we've done is we're regressing role functioning, or the natural log of role functioning, onto opiate use, pain, and PTSD. And then here at the end, I've just put a comma and specified beta. What this is going to do is it's just going to give us standardized coefficients, and as well as unstandardized coefficients in our output. So if we run through and run our command here, we see we get our regression model. A couple things to take a look, just starting at the top. We have our ANOVA table up here, giving us our sum of squares, degrees of freedom, and then our mean squared. Recall that our model sum of squares, this is going to be giving us variability that's attributable to our predictor in the model. So this is going to be literally the sum of the squared deviations between our predicted values for individual cases and the mean of y. So telling us how much above and beyond just guessing the mean our model is doing in terms of prediction. So that's our sum of squares model. Our sum of squares residual. This is going to give us the sum of the square deviations between our predicted values and our observed values. So this is our error. Okay, this is our total sum of squares. This is the deviation of our individual outcome values, or our individual y values relative to the mean, some of those squared deviations. And so this goes through, runs our ANOVA for our overall model, which is giving us a test of our R squared. Okay, and so if we go over through and we see here we've got 201 people in our data set. Here's our F value for our model based on our ANOVA table. Here's our P value, which is obviously very, very small, giving us very strong evidence here against the null hypothesis of an R squared value equal to 0. Here we see our estimate of our R squared. Looks as though this solution is accounting for about 38% of the total variability in the natural log of role functioning, so not too bad. And this is very clearly 0 is not a plausible population estimate for this, as indicated by our p-value here. Here we have our adjusted R squared. Remember that this is a better population estimate for our overall variability. We know that R squared is always going to be positively biased. Our adjusted R squared also going to be positively biased, but less so With a sample of 201, we don't have too much of a difference here. These are both pretty comparable, but just wanting to know what our individual output is here. Okay. If we jump down into our coefficients, we'll see here are our unstandardized coefficients for all of our predictors. This is our constant, standard errors, test statistics, p-values, and then over here, because we requested standardized coefficients with the beta option, it's giving us our standardized coefficients here. Okay, so first thing we want to take a look at is our constant. Okay, constant often isn't something that's super a big emphasis in psychological science, but just wanted to know what's going on with all of your output. Remember that your constant is going to be your expected value of y when all of your predicted when all of your predictors are held constant at 0. Okay, if we pop up, we take a look at our regression equation. We see that our intercept here, if we enter 0 for pain, 0 for opiate use, and 0 for PTSD, those all cancel out. What we're left is just our intercept here, and that's going to be our expected value of our outcome when all of our predictors are held constant at 0. Okay, so for this model, when opiate use is at 0, meaning no opiate use, okay, no opiate use, when pain is equal to 0, and when PTSD score is equal to 0, our expected value for our role functioning is going to be, the natural log of role functioning is going to be about 4.3. Okay, so if everything is at 0, this is what our model is saying our role functioning, or the natural log of our role functioning variable should be. If we go up to opiate use, now this is a little bit different because we've got, well, how about this? Let's go to pain first. If we take a look at our pain, our unstandardized coefficient for pain, negative 0.68. Okay. Now, if we were to have just a normal outcome that was not transformed, we would interpret our unstandardized coefficient as suggesting or indicating that for this model, a 1 unit increase in pain is associated with a negative 0.68 decrease in the expected value of role functioning. Okay, so again, 1 unit increase or decrease in your predictor and corresponding change in your expected value of your outcome. Now, a little bit tricky because our outcome variable here is a natural log. And the nice thing about natural log is they retain some level of interpretability. So remember that we walked through in class and talked about how if we have a natural log transform of our outcome or our dependent variable, we can then interpret that these unstandardized coefficients as for every unit change in x, corresponding percentage change in y. So with that in mind, what I can do is I can go through and I can take a look at my coefficient here, and I could say for every 1 unit increase in pain, I expect about a 68.5% decrease in the natural log, or excuse me, a 68.5% decrease in role functioning. So with that natural log transform, we still retain some interpretive properties here. If we go through, we see a very large t statistic, a very, very small p-value, giving us incredibly strong evidence against the null hypotheses that this coefficient is equal to 0. Okay. If we go down through, same thing. If we look at our PTSD variable, again, if we interpret this in terms of percentage change in role functioning, what we'll say here is that for every unit increase in PTSD, we're seeing an expected 1.3% decrease in role functioning. Now that might not seem like a whole lot, but if we look at the range of our pain variable relative to our PTSD variable, a 1 unit change in pain is much more than a 1 unit change in PTSD, and so that's why we're seeing very, very different magnitude of coefficients here. Okay. So again, if we were just looking at role functioning, our raw metric, we would interpret this as a 1 unit change or a 1 unit increase in our PTSD score corresponding to about a 1/100th of a unit decrease in role functioning, which wouldn't seem like a huge deal, but remember, because we're working with a natural log transform, we're going to interpret this as for every 1 unit increase in pain, we're going to see a corresponding 1.3% decrease in role functioning. Might not seem like a whole lot, but again, if we look at our t-statistic, this is clearly meeting criteria for standard criteria for interpretation. We have a p-value of 0.005, again providing some evidence, some reasonable evidence of evidence against the null hypothesis of this value being 0 in the population. So that gets our 2 continuous predictors. Then if we go through and we take a look at our opiate predictor here, now recall that opiate use is a dichotomous variable, 0 to 1. So if we're talking about a 1 unit change in opiate use, we're talking about going from no use to use, okay? And so here, what we would see, we would interpret this as we interpreted this as the difference between people who are using opiates and those who aren't. So this would suggest that we have about a close to a 4% reduction in role functioning for among individuals who are using opiates versus those who aren't, right? So if we go from no use to use, we're seeing about a 4% reduction in our role functioning variable. But if we go through and we look at our test statistic, it's quite small, our p-value is quite large, and so we really wouldn't probably make any sort of interpretation of this at all. Really, these data are inconclusive on whether or not opiate use holds any type of unique association with our outcome, and so we probably wouldn't do much in terms of interpretation here. But in general, when we're thinking about interpreting a dichotomous predictor within a regression model, we can interpret this coefficient as similar to the way we would interpret like a means-based test. We're saying that controlling for everything else in the model, we're expecting sort of whatever this coefficient is, difference between my 2 groups, okay? So here we have fairly strong evidence of a unique relation of pain with a natural log of role functioning, and a unique relation of PTSD with a natural log of role functioning controlling for other variables in the model. But what we also have here is our standardized coefficients. Okay, remember that it's hard to directly compare our unstandardized coefficients because our different variables have different metrics, and so a 1 unit change means quite a bit more, something different if we're talking about PTSD or pain. But what our standardized coefficients do, remember that our standardized coefficients basically run our entire regression model with z-scores. So we would take the z-score of the natural log of role functioning and regress it onto the z-score of opiate use and the z-score of pain, the z-score of PTSD. And what we end up with are standardized coefficients that correspond to a standard deviation unit change, expected standard deviation unit change in y given a standard deviation unit change in x. So if we were to give these literal interpretations, ignoring for the fact that we have a transform variable here, we would see that our pain variable, for every standard deviation unit increase in pain, we would expect a corresponding little over half standard deviation unit decrease in the natural log of role functioning. For PTSD, for every standard deviation unit increase in PTSD, we would expect a 0.16 standard deviation unit decrease in the natural log of role functioning. So we're seeing here a stronger magnitude of our standardized coefficient for pain as opposed to PTSD. And so what we conclude here is saying that in general for this model, looks like our pain variable is holding a relatively stronger influence on the natural log of role functioning relative to PTSD, although both of these, our model is giving us evidence for a unique effect of both of these variables. Okay, so this is what we get with our standard output in Stata. The one thing we might want to do is take a look at our effect sizes. So in Stata, the way we would do that, take our same model, our same variable list, natural log of role functioning on opiate use, pain, and PTSD, but instead of regression, we're going to substitute that with p-core. p-core is going to give us our partial correlations and our semi-partial correlations. So if we run this, we'll see that we've got now our partial correlations, semi-partial correlations, squared partial correlations, and our squared semi-partial correlations. Okay. Recall that our partial correlations are corresponding to the association between our predictor and the residual variance left over in our outcome after we control for other variables in the model. If we square that, we can talk about our partial correlation as a proportion of variance. So let's say for pain, we have a partial correlation of negative 0.56. But if we square that, we can say that based on these data, pain, our pain variable accounts for about 31% of the residual variability in the natural log of role functioning after we control for opiate use and PTSD. So after we section opiate use and PTSD out of the picture, what's left over in terms of variability that's not accounted for, pain accounts for about 30% of that, or about 31% of that. Same thing, our partial correlation. If we square this for PTSD, we see that PTSD accounts for about 4% of the residual variability in the natural log of role functioning once we control for pain and opiate use. So again, quite a bit smaller proportion of variability attributable to pain versus PTSD within the context of this model. So our partial correlations are nice, and we'll talk about this down the road, in that these are a nice measure of an effect with some standardized benchmarks. So we'll often report partial correlations as a benchmarked measure of effect size, but we also have our semi-partial correlations. And semi-partial correlations are nice because they're a little bit, the interpretation of our semi-partial correlations is a little bit more straightforward. This is reflecting the unique variability of our predictors with the total variability in our outcome. So here are our semi-partial correlations. If we square these, this gives us a little bit something a little bit different. So if we look at our pain variable, we see if we square our semi-partial correlation, we get a value of 0.277. And so what this would suggest is that within these data, pain pain uniquely accounts for about 27.7% of the total variability in the natural log of role functioning. Okay, so here with our squared partial correlation, we're talking about the residual variance attributable to a predictor. Here we're talking about of all the variability in the natural log of role functioning, pain accounts for about 27.7%, uniquely accounts for close to 28% of the total variability in our outcome once we control for opiate use and PTSD. Same thing, if we go down through, take a look at the squared semi-partial correlation for PTSD, we're seeing that PTSD uniquely accounts for about 2.6 of the total variability in the natural log of role functioning, so a much smaller percentage than what we got with pain. Okay, and then opiate use, we probably wouldn't make much of an interpretation on opiate use because we don't have clear evidence, actually very, very little evidence given our value here that is anything different than 0. So we probably wouldn't make too much of an interpretation there. So here we have our output. Here we have our effect sizes. So we're pretty good. The only other thing that we're going to do quickly here in this standard multiple regression, in our initial model, we had requested standardized coefficients. Here, if we just leave that option off and run this, what's nice is then Stata will give us confidence intervals for our unstandardized coefficients. So if we're looking, for example, at pain, our standardized coefficient is saying that our unstandardized coefficient is saying that for every 1 unit increase in our pain score, we're expecting about a 68.5% decrease in role functioning. But our confidence interval tells us that estimates in the or population estimates supported by these data range anywhere from an 82.8% decrease in neural functioning for every unit increase in pain to a 54.1% decrease in neural functioning for every increased unit in pain. Okay, same thing. We're just interpreting these coefficients the same as we've interpreted any other coefficient here. So this just gives us our confidence intervals. Okay, cool. All right, so that covers our simultaneous regression. But perhaps we want to look at the incremental benefit of each one of these as they add to the model. Now, this doesn't really make sense as kind of a contrived example, but just to show you how we would go through and set up these data in a hierarchical regression. What we're going to do is we're going to start by specifying nest reg, okay? And this is just going to give us a nested regression or a hierarchical regression model. So we put that, and then do colon, and then we just run our regression model. We're regressing natural log of role functioning onto opiate use, pain, and PTSD. Within these parentheses, you're just going to include whatever variables you wanted to. So let's say if I had biological sex, and I wanted to have biological sex and opiate use in the same in that first step, I would just go put opiate use and sex in that first one, and then we would have opiate use, sex in the first step of the model, pain in the second step, PTSD in the third step. We obviously don't have pain or biological sex in this data set, so we'll just leave it at that. But all we would do is just enter whatever variables we want entered at each step within this. And then just we'll go through and request standardized coefficients here. Okay, so if we go through and we run this, we get everything kind of stepped out. So starting at the first, we've got our first block that contains just opiate use in a predictor. So here's our ANOVA model and our coefficient table that just includes opiate use in and of itself. And if we just have opiate use in and of itself, opiate use alone in a bivariate regression model looks like we have very, very strong evidence of an effect here. Or sort of reasonably strong evidence of an effect here, suggesting that there's about a 23% decrease in role functioning across people who are taking opiates relative to those who aren't, right? And so a reasonable size standardized coefficient here. So if opiate use is the only thing in the model, we're seeing evidence for an effect, okay? But in the second block, if we go through and we add physical pain, we see something different. We see that our R-squared value with just opiate in the model going from 0.05 to 0.355. So we've got a big jump in our R-squared. So adding pain to the model does a much contributes a lot in terms of the prediction of variability in the natural log of role functioning, and we also see that now our opiate use variable is no longer meeting criteria for interpretation. Very little evidence that this value is there or that this has any sort of unique effect. So whatever portion of opiate use was predicting variability in our outcome, it looks like almost all of that was shared with self-reported pain severity. And so once we put self-reported pain severity is accounting for variability above and beyond opiate use. And so opiate use no longer brings anything new to the party. It gets washed out, but pain here is having a very clear effect. Okay. So in the last model, if we go down through, and this is a model where we've had PTSD in the mix, what we see is our R-squared has gone from 0.355 to 0.38. So we get a small increase in our overall R-squared. Here, we're seeing that opiate use still not contributing anything unique to the model. So its predictive value is assumed to be, we can't say that this has any predictive value in our model. Pain, though, continues to be a meaningful predictor here, in that it's contributing to the prediction of variability in our outcome. PTSD also demonstrating a unique association with the natural log of role functioning above and beyond what's being accounted for by pain and by pain and opiate use. A much smaller effect relative to ratings of physical pain, but it's still bringing something that's unique that's not being captured by pain, and so we're having evidence of a non-zero effect within this model. Okay, so in Stata, we'll work through each one of our individual regression, each one of our steps building on one another, and then here at the bottom, what we'll get is just a summary of our ANOVAs. So here is our F-test, degrees of freedom in the numerator, degrees of freedom in the denominator, and then our F value for our step 1 block where we just had opiate use. When we have pain in the model, what we see is, and again, this is looking at our change in R squared, and so we're seeing the change in our R squared from 0.05 to 0.355 associated with an F value of 93.48, and very clear evidence here of a substantial increase, non-zero increase in our R squared value from step 1 to step 2. And we're seeing that change in R square is about 0.30-ish, right? So about 30% increase from about 5% to 35%. So, and here's the change there. And so this p-value is associated with this change statistic here. Okay. Step 3 of the block where we add PTSD. Again, here's our F value, here's our p-value, here's our R squared, and here's the R squared change. So we get about a 2.6% increase in our model R squared. But our data are saying, so much smaller than what we got from step 1 to step 2, but our data are still saying that we have modest or moderate evidence for an increase in our overall R squared going from block 2 to block 3, as indicated by our p-value here. Okay, so coefficients across each block, and then we have our R squared change statistics here, down here in this final group. Okay, now the other thing we can do, because this output is pretty bulky, but a cool thing we can do in Stata is kind of condense this a little bit. So what we could do is, instead of just running our straight nestreg, what we can do is run some models and have Stata store those within this memory, and then kind of pull these together in kind of a nice set of tables. So what we're going to do here is, I've got nestreg, right? But then I'm going to say store each, so my hierarchical model, and store each one of those steps under the name role. Okay, and so what this is going to do is it's going to store output for step 1, step 2, step 3, and it's going to save those in models or in memory as role 1, role 2, role 3. Okay, so we're going to say run nestreg, but store each one of these models, and then quietly is just telling Stata to suppress output. Then we have our regression statement, just like we had up here, and then the no table is just telling Stata to suppress tables. So if we run this, it'll go through and it just gives us our last piece, but it went through and suppressed all of our coefficient tables here, right? What we can do is, once we've had it go through and it's run this model, and it's done it quietly in the background, but what we're going to do now is we're going to tell it Stata to create an estimates table containing role 1, role 2, role 3. Remember, this is in the memory saved each one of our steps. This is just some output. This is saying, giving us how many decimals we want our unstandardized coefficients B to be, telling it to give asterisks to p-values of 0.05, 0.01, 0.001. We're going to request an R squared value and sample size, and to leave the constant out of this. So if we go through and we run this, just pretty slick. what it's going to do is it's going to give us our unstandardized coefficient for opiate use in step 1, opiate use and pain in step 2, opiate use, pain, and PTSD in step 3, R squared at step 1, R squared at step 2, R squared at step 3, and then our sample size, which is the same. So just kind of a cute little trick, going through, changing up your output a little bit. You can just run the full thing if you want. Only other thing to note, that once you store things in your memory, Stata will just kind of keep it there. If I were to try and run, say, this model again after I've done it, you get an error. It says that it already has those results saved as roll in there. And so if we just use the command est drop and then an asterisk, whoops. What that's going to do is it's just going to clear it out. And now I could rerun this quietly, save my results. Now it's back. And then create my estimate table here if I want to do that. So just a couple slick things, different ways you can go through and pull this up. Hopefully this was helpful. Let me know if you have any questions, but this should give you resources to go through and work through these on your own. All right.